Well, good evening. Hello, everybody. Welcome to Space Oddities. Thank you for being with us on this lovely Tuesday evening. We hope you're all well. Hope you all had a fantastic week. And this week on Space Oddities, we're going to just finish off what we attempted last week when we were talking about the universe's biggest questions. And poor Daz had a problem with his video. So tonight we're going to answer the question, which we tried to do last week. How will the universe end? One of the biggest questions you could possibly ask. So we're going to be looking at that. We've also got other things lined up for you this evening, obviously. And a little bit later, we got some news of some changes we're making to the Space Oddities channel that we would like to share with you. So stay tuned for those. But in the meantime, I think we're going straight over to Daz and answer this question, Daz, if you would, of how will the universe end?
It'll pop.
It'll pop. Right. Moving
Okay,
on.
Thank you for that.
We're done. All right, we're done.
So there you are, Daz.
Right, okay then. We can just get rid of you lot at the bottom. That'd be great.
I've done that.
Right, let me just make sure I'm I've lost me presenters. Okay. Let's see if it'll do it from here. Right. Okay then. Right. So basically, yeah, we're sorry for what happened last week, and we've been trying to revive it, but there seems to be a problem somewhere along. It's got corrupted somewhere along the line. But as we were last week, we were talking about how the questions that astronomers are always striving to answer. Then what we were, one of the big questions that's always asked is, how will the universe end? Well, so basically, from humanity's earliest stargazing, we wondered not only how the universe began, but how it would end. Though the cosmos appears eternal, the physics eternal. Physics shows it is constantly evolving, and its fate will follow the same rules shaping it now. Cosmologists don't agree on a single ending. Instead, they study several scientifically grounded possibilities, some quiet, some catastrophic, some almost unimaginable. What follows are 8 serious evidence-based theories about the ultimate fate of all matter, energy, space, and time. Let's have a quick look at some of these events that possibly could mean the end of the universe. First of all, we have heat death, or the big freeze. The universe expands forever. Energy spreads evenly. The result is nothing can happen. We've got the big crunch. Expansion reverses, everything collapsed into a hot, dense singularity. The big rip. Dark energy grows stronger over time. Expansion accelerates uncontrollably. Galaxies, stars, planets, and eventually atoms are torn apart. Vacuum decay, the big slurp. A bubble of new physics rewrites reality at the speed of light. The big bounce. The big bounce. The collapse triggers a new big bang. The universe is cyclic. Proton decay. Matter itself slowly dissolves into radiation and particles. So let's have a closer look at each one of these. Heat death. Heat death is the leading theory for the universe's end because it follows directly from thermodynamics and cosmic expansion. As the universe grows, energy spreads out, stars burn through their fuel, and eventually no usable energy remains. Galaxies drift apart, star formation stops, existing stars fade, and even black holes slowly evaporate through Hawking radiation. Oops, sorry, didn't want to do that. Over unimaginable timescales, the cosmos reaches maximum entropy, dark, cold, and inert, with only thin particles drifting through an ever-expanding void. It is not a violent ending, but a gradual exhaustion. A universe that doesn't explode or collapse, it simply runs out of the ability to change, fading into an eternal silence. The Big Freeze. The Big Freeze is a colder, more experimental version of heat death, describing a universe that expands forever and grows increasingly empty. As space stretches, galaxies slip beyond view, stars burn out, and temperatures fall towards absolute zero.
Daz, may I just interrupt a second? There's a big problem with your sound. We can't understand what you're saying.
Yeah, it's really hard. Yeah.
Oh, okay. So,
No, that
hang
sounds
on.
fine. That sounds fine.
That sounds fine.
As you're talking now, it sounds fine.
So how long's it been like that?
About 30 seconds.
Okay, then. So I'll start with the Big Freeze again.
Yeah. Okay.
The Big Freeze is a colder, the Big Freeze is a colder, more experimental version of heat death, describing a universe that expands forever and grows increasingly empty. As space stre- Dear me. As space stretches, galaxies slip beyond view, stars burn out, and temperatures fall towards absolute zero. With motion and chemical reactions fading, life becomes impossible, and even matter is left as isolated fragments separated by vast silent distances. While heat death focuses on energy equilibrium, the Big Freeze highlights cosmic isolation, an ending defined not by destruction, but by endless separation, where the universe drifts into eternal cold and loneliness. The Big Crunch. The Big Crunch imagines the universe's expansion, eventually slowing, stopping, and reversing as gravity overtakes it. Galaxies begin moving inward towards space. Galaxies begin moving inward. Space contracts, temperatures rise, and collisions intensify until everything collapses into an extraordinarily hot, dense state resembling the universe's beginning. This fate depends on cosmic density and the behavior of dark energy. Current evidence makes it unlikely, but not impossible if dark energy changes over time. Emotionally, the Big Crunch is both violent and poetic, a universe dying as it was born, collapsing into a final singularity that erases all cosmic history. The Big Rip proposes that dark energy may grow stronger over time, eventually overpowering every force in the universe. As expansion accelerates, galaxy clusters break apart, then galaxies, then star systems, until even atoms are torn apart as space itself stretches beyond all limits. In the final moments, space-time ruptures and all structures dissolves. This scenario is especially unsettling because depending on dark energy's behavior, it could unfold relatively quickly on cosmic timescales. Emotionally, the Big Rip embodies cosmic horror, an ending where nothing can resist expansion, leaving no remnants or refuge, only total disintegration. Vacuum decay. Vacuum decay proposes that our universe may exist in a false vacuum, a higher energy state that could suddenly transit to a lower energy true vacuum. This happens If this happens, a bubble of true vacuum would form and expand at light speed, instantly rewriting the laws of physics and erasing all structures, particles, and forces. There would be no warning and no possibility of survival. Its unsettling power comes from its unpredictability. It could occur, it could occur trillions of years from now or at any moment. Vacuum decay confronts us with the idea that the universe might not end slowly or violently, but an instantaneous transformation that leaves no memory or meaning behind. The Big Slurp. It's a funny name, that one. The Big Slurp is a variant of vacuum decay in which a more stable vacuum state forms somewhere in the cosmos and expands outwards, consuming our universe. This new vacuum would have different physical constants, transforming all matter, energy, and space into something incompatible. Sorry. Something's going wrong here. Let's go back. Sorry about this. It's changed. I've lost my words. Changing all matter, energy, and space into something incompatible with our reality. The process would be invisible, unstoppable, and instantaneous upon arrival. The Big Slurp underscores our cosmic impermanence. Our universe may only be a temporary state, destined to be written by a deeper, more stable form of reality. The Big Bounce. The Big Bounce reimagines our Big Crunch as a transition rather than an ending. Instead of collapsing into a final destruction, the universe rebounds after contracting into a dense state, and it expands again, creating a new cosmos. In this view, the Big Bang is simply the latest cycle in an endless series of contractions and expansions. Quantum gravity theories suggest that extreme compression might trigger a repulse force, preventing infinite density and enabling the rebound. If true, the universe may never truly end. It transforms, with each collapse giving rise to a new beginning. The Big Bounce is hopeful, portraying a resilient, cyclic universe, though it raises deep questions about whether information or physical laws carry over from one cycle to the next. Proton decay. Proton decay envisions the universe ending through the slow dissolution of matter itself. If protons eventually decay, atoms and molecules will fall apart over timescales far longer than the current age of the universe. Stars, planets, and even stellar remnants would gradually disintegrate into radiation and elementary particles. Combined with ongoing cosmic expansion, this leads to a universe with no solid structures, only a thin haze of decay products spread across an endless void. It is a quiet, melancholic ending, but not sudden or violent, but a patient erosion in which everything, even matter, ultimately fades away. Each theory reminds us the universe is not eternal. It is in its current form. Change is fundamental. Even reality itself is temporary. The universe may end quietly, violently, or through renewal, but every scenario carries emotional weight. All remind us that the cosmos is a temporary and always changing. Knowing it has a beginning and an end makes the present moment meaningful. The stars shine now. Life exists now. And consciousness can wonder about its own fate. Whatever the final outcome, darkness, fire, rupture, or rebirth, the remarkable fact is that the universe currently contains beings capable of asking how it will end. The end.
Thank you very much, Daz. That's really good. Of course, you know which version of those, which theory you subscribe to, depends obviously on a lot of variables, and we don't have anywhere near enough data to say which one might be correct one way or the other. However, I just want to mention one, which is the idea of the false vacuum. I was reading this week that they've been doing some experiments with lasers, which seem to indicate that the idea of the universe just disappearing and settling into what's called a true vacuum state seems to be on the right lines, that it could actually happen. And basically what it means is we talk about the vacuum in space, but of course space isn't a true vacuum. It's at the quantum level, it's got virtual particles popping in and out of existence all the time. And that's called a false vacuum. And the universe might try to return to a completely empty state called the true vacuum. And if you think of a ball rolling down a hill and it gets stuck in a little ditch on the hill and can't go any further down, that's where the universe is at the moment. But the universe is trying to return to a much lower energy state, or it could return to a much lower energy state. And that could start happening at any second. But it's okay, because, as you said, that would create a bubble of nothing, literally nothing, that would expand, as you said, at the speed of light. So we'd be okay. We may be okay for billions of years. Or it could happen right next to us, and knowing how lucky it would. So yeah, it's an interesting idea. So thank you very much for that. Oh, my light's gone.
I remember the words of Mark Twain, who was looking at the Mississippi River. Right?
Of course. What
the
else?
Mississippi River winds and turns, as it flows, and because of that, the water hits those winds and kind of wears them down, and over time kind of straightens out the Mississippi a little bit. He said, based on that, the Mississippi River surely covered the entire planet at one time. Right? So we have to be a little careful when we extrapolate. I'll have to tell one more story. In physics class, I did my lab, and I got 3 data points out of it, and I fit a straight line to those 3 data points, and boy, did I get my hand slapped. Professors never fit a straight line to 3 data points. So we know they're all very interesting, but we have to be careful extrapolating.
Yeah, absolutely.
Barry's got a question in the chat if somebody would like to put it up.
Yeah, I'm on it. If scientists could trigger a false vacuum low energy state, would they?
Going from cosmology to psychology now, huh?
Maybe accidentally,
Would
Barry. I don't think they do it intentionally. But you would need. I think it would be well beyond our technology to create such a vacuum.
Well, a false vacuum lower energy bomb, if they did, would bomb them ourselves. We don't want them having that.
But Barry then goes on to say they thought the first A-bomb test might set the atmosphere on fire, but they did anyway. That's very true.
They thought the odds were remote, but actually, I'll be talking about a similar thing a little later. So.
Oh, okay. All right. Thank you for those observations, Barry. Thanks very much. Okay. Just before we move on, I want to tell you about a few changes that we're making to the Space Oddities channel, which we hope, we pray that you're going to like. Tell us if not. We've been very conscious of the fact that our Tuesday live streams are just seem to be getting longer and longer, and we want to try and cut them down in time a little bit, or perhaps a lot. For example, last Tuesday's live stream we ran for 2.5 hours, and while we love giving you this stuff because there's such a lot to give you in any one week, we're going to make a few changes to cut the times of the live streams down. So the change we're making at the moment, and there may be others, is that all the space news that I normally do on a Tuesday, we're going to move all of it, to our Thursday Space News Weekly video that we produce and publish on a Thursday. Normally publish it on Thursday evenings. So all the space news will be all together in one place in that, or at least the major stories. So that's one change we're going to make, as I said, and there will be others. But we are conscious of the fact that we do drone on a bit too long sometimes. So your feedback's appreciated. What do you think about that? Put it in the chat. Obviously it does mean you're going to have to watch a separate program to get the space news, but at least it'll be all in one place, and you'll know that it'll be there on a Thursday. So if you have any thoughts about that, any views, then please put them in the chat, and your views, obviously, as always, are much appreciated. So let's move on. We're going to move over to Dave now, and Dave is going to give us his wonderful weekly feature to tell us what's been happening this week in history.
Okay.
So Dave, over to you. Let's put
Yep,
that up for you.
It's grinding. It's trying to share my window right now. Okay, there we go. All right.
Have you got the slideshow on that, Dave?
Let me do it that way. Yeah. Okay.
Yeah, do it that way.
Right. Okay. There we go. All right. Okay.
Can't see it.
Yeah, that's better. All right.
And we can't
share.
There we are. That's got it.
You're good?
Got it.
Okay.
Yeah.
Okay.
We're good.
All right. Okay. So, actually, so a couple things that are in this week in space history we're going to be talking about in more detail later in the program. So some of this I'll go through a little quicker than normal, but okay. So April 26th was a good international day, I guess, in history. Interestingly, the very first international satellite launched, which was Ariel 1, which was a UK, basically mostly British-built satellite launched by the United States. And actually, the Ariel satellites went on to have a really long, early in the early space program, a really long run, a bunch of Ariels, and they did a lot of the very, very earliest space weather and heliophysics and space physics type of research and upper atmospheric research, and again, very, very successful missions. 1967, the very first launch off a sea-based platform. San Marco 2 was actually a satellite built by Italy and launched by the United States off of a platform that was off the coast of Kenya. And again, another successful collaboration really between two countries. Cassini-Huygens, of course, the European Space Agency and NASA joined to do this mission. And this was the Venus flyby on its way to Saturn. It had a few Earth flybys, Venus flyby, and in 1998 on April 26th, it flew by Venus and got to test out a lot of its equipment, which was always a good use of the flybys, besides the nice gravitational boost that you get. And 2023, April 26th, was the Japanese Hakuto R mission. Contact, unfortunately, was lost. It attempted to land on the moon and failed. Contact was lost. Again, it's hard. It's hard, right? Landing on the moon is really tough. And so, yeah. All right. Here's one that I'm going to talk about a little later in a little more detail, but it was 55 years ago today that NASA announced it was the end of the quarantine program for astronauts. And you probably remember like similar pictures to the one that's up there now of the Apollo astronauts looking out of the window after they'd gotten back because they weren't allowed to have contact with the rest of humanity for 21 days because of a quarantine. And like I said, I will talk about that in a little more detail a little later. But it was 55 years ago today that was finally ended. They finally decided it was safe for the astronauts just to come straight out of their capsule and join the rest of us. Okay, this may not seem like a so much of a space exploration thing, but actually it really did change the way. Okay, well, first off, yeah, let me say that this was the first meeting of the French Academy of Sciences. It was done at the Louvre. That's a nice place to have your first meeting. They before this time, not this very date, April 29th, but before this time, it was really more common for science to be funded by rich patrons, by royalty. Galileo was sponsored by the Medicis, things like that. It was starting to change now. Science was A, becoming kind of big, and B, governments were starting to see the advantage of funding science. So these science academies were really crucial in sort of guiding, making decisions about what should be funded. Now we have a government which is going to fund some science. Okay, the government itself, they don't know what to fund, right? I guess the way that the princes and the rich patrons just would fund things that they were interested in, but the academies would guide, and still do. Actually, we have these decadal plans for NASA now that come out every 10 years that say, here's what NASA should be focusing on for 10 years, put together by scientists. And that's what these academies would do. One of their many functions, of course, was to guide the government. And so really a space program, at least in when we first started the space program, was only be done by a government. We may be going back to the rich patron system now. I'm not sure.
Hey, can I just interrupt a second? We've lost your presentation.
Is it?
What's that?
Your presentation is gone.
Oh, you're kidding me.
Who keeps putting that?
That's what's in there. No, sorry, it's the wrong one.
Oh, it disappeared from the. Oh no.
Yeah, it's gone again.
Ay.
You want to try again?
Yes, I will. Oh boy, this has happened. All right. We tested it out. And I thought
on your machine somewhere.
While you're sorting that out, I'd just like to tell you a story about, you were talking about Ariel 1 being the first satellite launched by the USA and the United Kingdom. Well, the day before they launched that, the American Navy conducted experiments in the Pacific by exploding nuclear bombs, and in an operation called Starfish.
Yep.
And what happened was Ariel 1 flew into the radiation that it left behind, and it completely scrambled its gubbins, although it did actually give some data back, and it was operational for quite a few years later. So just a little bit of history to go with that.
There was a group of satellites that were victims of Starfish 1. Because they didn't really realize it actually formed basically a radiation belt, and any satellite that happened to be in the way ended up getting damaged to some extent or other. So that's true.
Because Telstar was launched a few days later and suffered the same fate.
That's right. And there's 3 or 4 other ones I remember, and I don't remember the names, but you're right. There were a bunch anyway.
Mm-hmm.
Yeah. Oh well, so we helped the British launch a satellite, and then we blew it up. I don't know what to tell you. All right, April 29th, 1954, the first launch of a 3-stage rocket from Wallops Island. And this was NACA at the time. NASA hadn't formed yet. This NACA. NACA, yes, the National. Advisory Committee on Aeronautics, National Advisory Committee on Aeronautics, right? And it turned out that there were a lot of these Nike boosters. So this was a Nike booster on top of another Nike booster with a Deacon sounding rocket on top. And there were a lot of these Nike boosters lying around because they were overcome by other boosters, and the Army wasn't using them, or the military wasn't using them. So there were a ton lying around. So actually at Wallops, they would take these things and launch all sort of stuff on them just because they had all these Nikes lying around. So they tried sticking a couple of them together and putting another one on top of them, and it worked. And they got the first 3-stage launch in 1954. All right.
They should have stuck with, it's gone again, Dave.
All right. Oh boy.
For our audience, when you're buying us coffees, if you could chip in a little extra to get Dave a good laptop, that would be
great. I guess so. That's my thing this week, I guess, is I gotta get a new one.
Just don't buy us a coffee, buy us a laptop.
June.
Yeah.
Yeah. Well, maybe we're
set up
pushing,
a
we're pushing it there, I guess.
for Dave.
Do you want to try? All right, I can share it one more time and talk fast, but
Yeah.
this may be a problem later. But you should have my presentations. I uploaded them, so if you can show my next one from there.
Well, let me
That
just
would be
turn
better.
this back on. What I suggest is that you don't run the screen show. We do it from the window. Let's put that back on.
Oh,
Hang on.
okay. I don't know if that makes a difference, but here, all right. Let me.
Well,
Well, here
let's
we go.
Try again. Try again.
Okay. All right.
Apologies for technical problems.
I'm sorry. Yeah. Okay. 1006, April 30th, the brightest supernova in recorded history, supposedly about as bright as a quarter moon. You could see it during the day. It cast shadows at night. They estimated it as a minus 7.5 visual magnitude. They believe it was a type 1A. It's a spectacular sight in the sky right now, and it's particularly spectacular is that that up there at 12, 1, 2 o'clock position is this giant shock wave. It's just pushing. It's just run into a bunch of interstellar gas and dust, and it's just shoving it all together and forming this. It's causing it. It's energizing it. It's causing it to glow, and it's forming this shock wave. And you can even see it appears to the eye that it's actually slowing down the expansion at that one little section of the supernova, but I'll leave that to the astronomers. Messenger mission ended on April 30th, 2015, after 4 years in orbit. Taught us huge percentage of what we know about Mercury.
What a great mission that was.
Yeah, that was a spectacular mission. And I remember when they were planning it at Carnegie Institution. That was pretty cool. All right, near and dear to Lou and my heart, May 1st, 1959. Goddard Space Flight Center, what was Beltsville Space Center, was established as NASA's first space flight center. And there's some images putting up the first sign, and just some images from the early Goddard.
So is that building? Dave?
That's building 1. Yeah,
that's
that was
building 1. Yeah.
Yep. They
Wow.
cleverly named the buildings just building 1, and the first one they built, then building 2. Building 1 is still standing. Building 2 they took down some years ago, but 3, 4, some of the buildings are still up. The old buildings, yeah. Spirit became permanently stuck in the soil after over 5 years roving on Mars, and over to the right there is them. It's just sort of wiggling the wheels there. This is part of their effort to try to get it to be free. It broke through some duracrust, which is just a thin layer of more solid type of material, but once it broke through, it couldn't get out. It had 2 wheels already that were inoperable by that point. It was actually driving backwards at that time because the 2 front wheels had both frozen up or stopped working, and so they had to drag the front wheels along just by driving backwards. But an incredibly successful mission. I mean, just looking at the picture at the lower left there, it's like what an incredible mission.
Well, considering that they estimated the rovers only had about 90 days.
Yes and no. Yeah, I mean, they would always greatly, sort of underestimate that lifetime because they wanted it to be successful, and they didn't want to say it's going to last 2 years, and if it lasted a year and a half, so the mission's a failure. So the 90 days was I don't think anyone really thought it was going to only last 90 days. Still, 5 years is amazing. I'm not taking anything away from that. But it wasn't quite that, that amazing. But okay.
Was Spirit the sister of Opportunity?
Yeah.
Yes.
Yeah, I thought it was.
Yeah. And Opportunity. Yeah, and now I don't even remember how long Opportunity went, but that lasted longer, right? That was quite a long.
Yeah, much a few years longer, I think.
Yeah, and to lead into our next subject, TRAPPIST-1, May 2nd, 2016. So 10 years ago.
Wow.
Yeah. TRAPPIST-1. We saw the first really bunch of Earth-like planets ever, and not around a sun-like star certainly. But you'll hear more details about that. Yeah, but I don't know. I remember that. I bet we all do when they announced that. It was pretty exciting, and it really led to a lot of all sorts of speculation and science fiction-y types of stuff, but I thought it was just great imagining all these Earth-like planets. Anyway, all right, there you go. They're all about 75 to 110% size of the Earth, and 0.01 to 0.06 AU, very close to the star, but a very dim star, so it's in a habitable zone. All right, thank you.
Thank you very much for that, David.
Thank you, Dave. Yeah, thank you.
Apologies for the slight technical.
I'm sorry about that. I will have to figure
No,
this
that's
out.
all right. We'll get you a new. In fact, Ian McIntyre has already donated a couple of pounds to the Buy Dave a Laptop Fund. So
No.
yeah, so,
Dave Memorial Laptop Fund.
yeah.
Okay.
So,
Wow, thank you.
Thank you for that generosity. In fact, thank you for all the generosity this evening so far. But we're going to name it the Dave Williams Laptop Fund, and we're going to do a commemorative mug, and get the new laptop.
All right. We'll have a little ceremony for my old laptop, I guess.
Are we going to do a GoFundMe page?
Yeah.
What a great idea.
Yeah.
It gives Dave's old computer a Viking burial.
You'll be our poster child, Dave.
Oh boy.
Go for
Oh
it.
boy.
Definitely. All right. Thanks for that, Ian. Thank you for kicking off the fund for that.
Thanks, Ian.
Yeah, very much. I also want to say thank you to because this should make me feel even better. Good old Ian had already given us a donation this evening, but when he saw your plight, he had to donate again.
Oh no.
So there we are.
And Barry's just done the same.
Wow.
$4.99.
Oh, thank you, Barry.
Gosh, thank you guys.
We're well on the way.
we've hit onto something here, huh?
Yeah. Actually, my computer's been playing up a bit recently.
Nice try, Andy.
Yeah.
I could use a new aerator, actually.
My computer keeps making a humming noise.
That's because it doesn't know the words.
Yeah.
So anyway, I want to put a comment up that Barry said about the Mars exploration rovers. They thought the Martian dust would clog the gears, but instead it acted as a lubricant. So interesting. I didn't know that. Thank you for that.
I didn't either. But
there you are. All right. So anyway, Dave talked about the TRAPPIST-1 system 10 years ago. Unbelievable that they made the discovery. So what I would like to talk to you about is the TRAPPIST-1 system. Now, just let me get this up on the screen, and I will share this with you. And this will actually work. So let's just get this up. There in a second. The old Steam computer. There we are. Okay. So the TRAPPIST-1 system. The TRAPPIST-1 system is a star system, as Dave said. 7 planets have been found in it, and the interesting thing about the TRAPPIST-1 system is that they're all sort of fairly Earth-sized, and some of them lie in the habitable zone, which means that there's a possibility, or we've thought there was a possibility, that they might have the right environment to sustain life. So let's have a look at it. So let's do it first of all with the word TRAPPIST. Now, the TRAPPIST name, you may have heard of the Trappist monks of Belgium, who are famous for brewing incredible beers, and I've had some, and they are truly and they, one night after drinking too much of their beers, they got really drunk and decided to build this observatory called TRAPPIST, which is a complete lie, of course, but I thought I'd give it a go. You can laugh if you want. So anyway, the TRAPPIST system, TRAPPIST is an acronym, predictably, and it stands for Transiting Planets and Planetesimals Small Telescope. It's at La Silla, as part of the La Silla Observatory Complex in Chile. And as you can see, it's actually quite a small telescope. Well, it's bigger than mine, but you know, it's not a competition. So this made the discovery 10 years ago of 2 exoplanets orbiting the star that was then named TRAPPIST-1 because it was the first discovery. So first of all, we're going to have a look at the star. Now, the TRAPPIST-1 star, it's an ultra-cool red dwarf star. As we've mentioned before, red dwarfs are the most common type of star in the galaxy. They're small, but perfectly formed. They are ultra-cool. And for example, TRAPPIST-1 has a surface temperature of 2,556 Kelvin. The sun is about 6,000, as we know. The interesting thing about red dwarfs is that they are prone to rather violent flares, which is not good, obviously, for planets that might contain life. The other thing about the 7 planets is they're all, by solar system terms, in solar systems, they're all very close to their star. So we're looking at a star that's 40 light years away. That's 25.3 trillion miles. The spectral type, in case you're interested, is M8V. It's got a mass only 8.9% that of the sun, and its radius, student diameter, 24%. It's about a quarter of the sun's diameter, but it's very dim. Its luminosity is only 0.0525% of the sun, so it's a very dim star. Now, it's reckoned to be about 7.6 billion years old. It's got a similar metallicity to the sun, and that is to say elements that are heavier than hydrogen and helium. It rotates once in 3.3 days, and it's very active because of these flares and sunspots. So these planets are, they're going to suffer a lot of radiation from this star. Let's now move on to have a look at the actual planets themselves and whether we think they can support life. Now, I'm going to go fairly quickly through these. So let's go to have a look at the system as a whole. So you've got the TRAPPIST-1 system, 7 planets. Now, when astronomers discover exoplanets, they're given a letter depending on the order outwards from their star. So the planet closer to the star is B, the star itself is A. So the one closest to the star is B, the next one C, and so on. And in this case, because there are 7, that goes right out to H. There is a habitable zone, of course, in this system, and that consists of that contains 4 planets. Now, if we just have a look at the system overview, it's an ultra-cool red dwarf, as I said, 40 light years away, 7 planets discovered, as Dave said, 10 years ago, discovered by the TRAPPIST ground-based telescope in Chile. And then this is the orbital layout, looking down on the top view with B, C, D, E right out to H. Those orbits are not to scale. And we're going to have a look at the individual planets. So obviously the place to start is B, which is the closest star, closest exoplanet to the star. 4 of these planets are in the habitable zone, so we're going to look at those as well. Now, TRAPPIST-B, the innermost world, is it's about the same size of the Earth, 0.92 relative to the Earth. It's got 0.85 Earth masses. So we're looking at, in terms of size and mass, we're looking at a planet that's very similar to the Earth. 66% of Earth's gravity, given obviously if you take 0.85 Earth masses, that means lower gravity, 66% of Earth's gravity. It's a rocky terrestrial planet. It orbits that star in 1.51 Earth days. So it really whips around the star. And obviously because it's very, very close to it. It's tidally locked so that the same hemisphere always faces the star. It's possibly got volcanic activity because it's very hot being that close to the star. We don't know if it's got a magnetic field. The JWST has said that if there is any atmosphere around that planet, it's likely very, very thin with a pressure of less than 1 millibar. No detection of any atmospheric molecules. So, it probably hasn't got an atmosphere because of the intense stellar radiation and high temperatures. It's too hot, far too hot, and too close to its star to support life as we know it. So we can say almost categorically this is not a suitable planet for life. And let's move on to C, the next one out, the second one out from the star. Again, very similar to Earth radius, 1.10, 1.16 Earth masses. So again, you're looking at a planet that is, more or less exactly the same size and mass as the Earth. Its surface gravity is 81% of the Earth. It's another rocky terrestrial planet. It orbits the star obviously longer than B. It orbits in 2.42 Earth days. It's got an extremely hot dayside temperature because, again, it's tidally locked, meaning the same hemisphere always faces the star, same as our moon is tidally locked to the Earth, and we always see the same side of the moon. The surface temperature estimated at 430 to 630 degrees Celsius, which I think you'd agree is pretty hot. What else can we say about it? Again, rocky surface, possible volcanism, not known if it's got a magnetic field, no substantial atmosphere detected. Potential for life is, again, very low. Too hot, no liquid water because of the high temperatures, high levels of stellar radiation, frequent flares, not a good planet to get life going. And obviously, it's not in the habitable zone. If we move out to D, then again, it's a bit smaller, 0.77% of the Earth radius, only 0.3 Earth masses, though. So it's not as dense as the Earth. And it's only got 0.57 or 57% of Earth's gravity. Again, it's another rocky terrestrial planet. It orbits in 4.05 Earth days. It's probably, although we don't know definitely, probably tidally locked. It's probably got a rocky surface, likely covered in silicates and minerals. No magnetic field detected. We don't know if it's got one or not. But it does have quite a substantial atmosphere. But it's not, it hasn't got a substantial atmosphere. And again, if it has got an atmosphere, the pressure is less than 1 millibar. No detection of key atmospheric molecules like water, carbon dioxide, ammonia, nitrogen dioxide, none of those found. Intense stellar radiation, but it does lie on the inner edge of the habitable zone. Although high surface temperatures would obviously make this liquid water unlikely. But perhaps on the far side of the planet, perhaps it's a bit cooler, perhaps liquid water could form, but it's unlikely. So again, sort of low to moderate possibility of having life. If we move to E, again, almost the same size as the Earth, little less dense, only 0.77 Earth masses, 61% of Earth's gravity, again, a rocky terrestrial planet, orbits in just over 6 Earth days, probably, again, tidally locked, silicate rock and minerals on the surface, not known if it's got a magnetic field. This one has got a substantial atmosphere, so this is quite hopeful. And but the only thing is, it's not, we haven't detected any atmospheric molecules, again, the same thing as carbon dioxide, water, ammonia, nitrogen dioxide, that sort of thing. But again, it's very close to the star relatively. But it's not impossible that life could start there. The surface conditions could theoretically, because it's cooler, with the temperature being lower, it could conceivably have life, but again, it's not likely, unfortunately. If we move to F, again, we've got a planet that's almost the same size as the Earth. It's 93% of Earth's mass. It's got 78% of Earth's gravity, another rocky terrestrial planet, orbiting in just over 9 Earth days, probably again tidally locked. Again, a rocky surface with silicates and minerals, not known if it's had a magnetic field. And again, if there is any atmosphere present, it's got a pressure of less than 1 millibar, no atmospheric molecules detected, intense stellar radiation preventing the formation of a substantial atmosphere, but it's in the middle of the habitable zone. So conditions may allow for liquid water. If there is an atmosphere and there are other mitigating factors exist, it's not inconceivable there could be liquid water. It's promising but uncertain, and this is rated as moderate potential for life. And if we move to G, this is so it's the same one, no. G, again, almost the same size as the Earth, tiny bit more mass than the Earth, 93% of Earth's gravity, rocky terrestrial planet. This is, getting repetitive now. The temperature is very cold, though, because this orbits in 12.35 Earth days. And it's likely very cold because we're now going on the outer edge of the habitable zone, and it's estimated to be minus 72 to minus 46 degrees Celsius. So because it's that much further out, it's actually very cold, likely tidally locked, silicate rock and minerals surface, not known if it has a magnetic field. If there's an atmosphere, it's very thin, no atmospheric molecules, and it's likely too cold to support life as we know it. So there's unlikely to be liquid water because of the low temperatures, and it's got a low potential for life. And lastly, the most distant planet from the star, G, tiny bit bigger than the Earth, a little bit less mass, 71% of Earth's gravity, a rocky terrestrial planet again, silicate mineral surface. We don't know if it's got a magnetic field, very thin atmosphere if there is one at all, no atmospheric molecules. It's far outside the habitable zone. It receives very little stellar energy. Now, don't forget, if you're thinking to yourself, well, hang on, these planets are orbiting in days, how come they're so cold? It's because the star is very cool. That's why. If the star was hot as the sun, these would be too hot for life, far too hot. But because the sun is putting out so little energy, even though it's only orbiting this one in nearly 19 Earth days, which would indicate it's close to the star, but of course the star is very cool. It's not putting out the heat. So this is why the H planet, which is outside the habitable zone, is probably too cold to support life. And there you have it. So the interesting thing about the TRAPPIST-1 system is that we were quite optimistic for a while that at least one of those planets would be a good place to find life, but it now looks as if that's not the case, which is very disappointing. On the other hand, it's the only star system we found where there are 7 terrestrial planets, where all of the planets are terrestrial. So it just goes to show that the universe can do it when it wants to. It can create rocky planets, and moreover, rocky planets almost exactly the same size as the Earth. So I wanted to tell you about that this week because the data from the James Webb Space Telescope that studied all of these planets, it's now been released in its entirety, even though the observations were done a couple of years ago. And the reason for this is that time on the JWST telescope is very competitive, and you have a lot of research projects clamoring to get time on the JWST. Like the Hubble telescope, it's well oversubscribed, and the Space Telescope Science Institute ultimately makes the decision of who gets the observing time. But a lot of the research projects at universities, they don't want to release the data they've collected in case they get scooped before they've had a chance to do all the research and write their papers. So they've been hanging on to the data and not releasing it till they've done all the research, written all their papers, and then they release the data. This sort of proprietary data is not uncommon in science, because obviously if you're a university that's funded observing time on the telescope and you're funding all the research, the last thing you want to do is to get scooped by somebody else. So this is,
comment on that, Andy. Throughout the federal government, but certainly for NASA, there's a real push for open science, open data, open research.
yeah,
Which means, among other things, that the proprietary periods for data coming down from new instruments is getting shorter and shorter, and in some cases evaporating.
right. Well, that's good, because there's a move towards open data across all of science, especially where science publications are concerned.
Yeah, I know there's on the James Webb, there are some that proprietary data is held back for a period of time for some systems, but for Gaia and Vera Rubin and everything, it's literally open source. Anybody can actually gain access to it, and so it's the more open it is, then the more people can get hold of it and do their own little thing with it, because they're all doing different things. So
now there's a problem with that. There's still a problem, even if you release the data immediately. Let's say you calibrate it, you geolocate it, or whatever needs to be done, and you release it. The research findings are published in Nature or Science or Icarus or whatever the peer-reviewed journal that you have is, and those often require subscription fees. So that's also a problem in open science, is actually getting to the data, getting to the research once it's been published. So I just want to make that point.
Yeah, because I think this is the Vera Rubin. The information that comes down, as Andy says, it produces millions and millions of texts every night. But what they are is they're sent off to several what they call brokers, who actually do the sorting, and they're the ones who people have to apply to get the information and the data that they require. So how that, I don't know if they've got to subscribe to that or not. I'm not sure.
Yeah. I mean, the brokering system is all automated, and there are lots of different brokers that, as you say, filter and direct the data to the right people. Anyway, as I said, this is why I wanted to talk about TRAPPIST this week, because the last of the data for TRAPPIST has been released, and everybody was hoping right to the end that there might be more data that indicates that at least one of these planets will be more habitable than it actually is. But because the red dwarf planets, red dwarf stars, are the most common in the galaxy by far. It means that a lot of star systems with planets in the galaxy, and presumably other galaxies as well, not just ours, they might have planets that on the face of it are suitable for life, but they just keep being zapped by extreme levels of ultraviolet radiation. So we can probably write off an awful lot of star systems as having life, simply because the planets orbit a red dwarf. So there we are. A bit sad, but we will get there one day, I'm sure. We will find a planet with life on one day. I think more likely is going to be that we find life within our own solar system long before we find life on exoplanets. But maybe, I don't know. Time will tell, as they say. Anyway, you may be asking yourself the question, based on what I've just shown you, that how can we possibly tell firstly, if an exoplanet has an atmosphere, and secondly, what's in that atmosphere? It seems like magic that we can look at planets that are trillions upon trillions of miles away and say, oh yeah, that's got ammonia in the atmosphere, or helium, or hydrogen, or whatever it is. And Lou now is going to tell you exactly how they do that, how astronomers can actually manage to analyze the atmospheres of planets that are so far away that, you know, even with the biggest telescopes and the closest exoplanets, they still appear fairly small dots. So how on earth can we analyze their atmospheres? And this is an absolutely fascinating story, which Lou is now going to unveil to you.
Well, the truth is, you know, we have no idea. It is magic, in fact.
All right, moving on.
Not that many years ago, a few decades ago, it was thought to be unachievable that you could even detect extrasolar planets, much less characterize their atmospheres. So, as they say, we've come a long way, baby. And what we're really trying to do, let's be honest with ourselves for a moment. We are terrified. Humanity is terrified that we might be alone, right? It's the existential anxiety and existential despair. What if we are it? So we look for other planets, other places in the universe that might have life, that might kind of keep us warm and cozy at night, right? So it turns out, move on a little bit here, that planetary atmospheres are probably the single best indicator of whether an exoplanet might be habitable or might have life. Is it taking a while to come up on your end here?
Yeah, it is. Yeah.
Okay. We'll just be patient for a moment.
Mm-hmm.
Well, some of us will be patient. Some will be screaming inside. I'll be screaming.
I'm screaming inside, Lou.
We'll take up a fund for you, Lou.
Yeah, we might. Yeah, look at that. Well, I'm running it from the restream, so. Let's see if I can go to the next slide.
Okay. Yes,
No?
there's an icon there saying the image is broken.
The image is broken. Well, isn't that lovely?
Mm.
Okay, let's go back to the first one. The first one is great.
Right.
All right.
Tim. Try and
And
move forward again.
second one,
I presume it's okay on your screen, is it?
I don't see it I'm on restream. I don't see it.
But on your screen, on your computer, you see it.
Oh yeah, on my computer. Yeah, it's fine.
Right. Okay.
Hell, well, I may have to let's see if any of them are okay. Let's go to the fourth one. It just doesn't like my presentation.
What a shame.
What a shame.
All
Well,
right.
I can talk.
Well, we'll try and bring that to you later.
No,
so,
I'm sorry.
Moving on, we're having a lot of fun tonight, obviously. So we'll try and bring that to you later. And we'll give that a go again a little later. So we'll move on now to our next topic for this evening. And now we go over, as tradition dictates, to Roger, who's on mute at the moment, not anymore. Okay. So we're going to have a look, as always, at what's in the night sky and this week's viewers gallery. So take it away, Roger.
Hey, so here we are working our way through April into May now. So how time flies. So we're working our way out through to a full moon on Friday. So if you're going to do any astrophotography, you need to go narrowband, I'm afraid. But there we go. That's how it is. But looking at the night sky, we've still got a hint of Orion, depending on what time of the night sky you're looking at. But it is unfortunately fading out into the western horizon. But we do have Gemini, with Jupiter still dominating the western skies. And also we've got Leo and Virgo coming up through with loads of galaxy clusters available. But we've also got a few summer constellations gradually appearing through the night. And obviously we'll be able to start to see the arch of the Milky Way coming into view more prominently, which is nice to see and a good photographic opportunity. But before sunrise, we've got Saturn, Mars, and Mercury. And then trailing on behind after sunrise, we've got Uranus and Venus, which we all know and like to see in the evening skies soon after sunset. So that's looking pretty good. But there is an opportunity, although it is probably a bit late for us in the Northern Hemisphere. We've got Comet C26A1 MAPS. It's currently running through Orion at the moment, but obviously by the time it gets dark, enough of Orion is probably set for this not to be really visible, although it might be only a couple of degrees up above the horizon when the opportunity might arise. But there is a comet available for us, but it's not particularly bright according to the calculations on this table here. It's currently about magnitude 11.4, and then it just fades away to a more dimmer visibility, but that will be not really visible for us, unfortunately. We do have more solar activity at the moment. As you can see, there are quite a few more sunspots available than we have had over the last week or so. And if you look to the far right image, we do have a coronal hole coming towards Earth facing in the northern part. So there may be some interesting opportunities for some aurora. We do have a good gallery this week. It is a bit lunar based, but that's how it goes. So our first image is from Michael Murphy of the Whale and Hockey Stick galaxies here. And here we have the image that he has provided. Ooh, hang on. That went a bit quick. So the whale on the top and the hockey stick down below.
It's lovely.
Can we also...
Love
How
it.
do you get a hockey stick out of that?
That's fantastic.
Yeah, it's beautiful.
It's a beautiful picture, yeah.
Yeah.
Well captured. And then we move on to one of Lou's Sea Star 50s on an equatorial mount of some things that we have here of M81 and M82.
That's nice.
Oh,
Nice,
that's
Lou.
enough.
Might be a little
Yeah.
over-processed, but
That's fine. You can
it's well
certainly
out.
see the spiral arms nicely.
Yeah.
Exactly, yeah, it's lovely.
Beautiful.
Well done.
Um,
And not to be content with just one, he's put a picture of a moon through his cell phone on a C11.
Oh, that's all gorgeous.
I was out at
Wow.
the observatory. I didn't feel like hooking up the big equipment and all that, so I just took my cell phone and took a picture. It turned out okay.
very well. Yeah.
Very nice.
It did.
Yeah.
Well done. Thanks, Lou.
Mhm.
And then there's some pictures that I took on the 25th of the moon. Some
Oh my
closer
God.
detail pictures.
Nice.
Beautiful.
Nice.
So I thought I'd try and
Lovely.
do some closer views. Yeah.
That ain't no sea star image.
No.
Yeah.
No, that was just with my 5-inch refractor.
Wow.
Very nice.
Turned out quite nicely. And if we manage to zoom in, you can see Hadley Rill, which was the site of the Apollo 15 landing. And so that was
I mean,
quite
the
good.
definition on those mountains is fantastic. It's lovely.
Fantastic, isn't it?
Yeah, and the
Yeah,
Alpine valleys come out quite nice as well.
Yeah, very nice.
What kind of 5-inch refractor do you have?
It's a ZWO 130 millimeter, but it's made by Ascar.
Oh,
under their
Ascar.
brand.
Yeah,
So-
they actually started making some really nice refractors.
Oh
Outstanding.
yes. Mm,
Okay.
Yeah, and in the left,
Right.
you've also got some nice coloration as well.
Yeah.
yeah. And we've got a few images from Kenneth Holmedal in Norway.
Oh, that's gorgeous.
And
Wow.
I did tell him to send me some because he was getting some phenomenal aurora, and these were all quite recent in the last week.
Oh, that's nice.
Yeah.
Yeah, it's not fair, is it?
I know it's a bit off the topic, but that last image, the one with the aurora through the clouds, reminded me of Independence Day when the aircraft, the spaceships were coming into the atmosphere.
Yeah. This is another one, but this was done on his mobile phone.
God, that's gorgeous.
Wow. Oh, there's Cassiopeia, yes?
Yes, there is. Well spotted.
It is, yes.
Wow.
Yeah, just saying.
So that means that Andromeda is just below.
It's beautiful.
Yeah, it'll be actually in the aurora, won't it?
Yeah.
Yeah.
Probably.
It's fantastic.
And then he did a moonshot with his Olympus camera. And this was what he managed to get.
Oh,
that's
wow.
Gorgeous.
Beautiful. Lovely colours.
Yeah. Got some good mineralization on that one.
Mm-hmm.
That's gorgeous.
And then to top it all, he got a sunset with Jupiter, Moon, and Venus with a hint of aurora on his cell phone.
Oh, he's just showing off now, isn't he?
Yeah.
Oh, that's a keeper.
That's lovely. That's lovely, Kenneth.
Yeah.
Thank you for that.
Kind of has an unfair advantage with that aurora all the time.
I know. Sometimes he just sees it out of his living room window. You know.
Doesn't even bother going out.
No,
I would never aurora.
I just use my crayons on my images. I don't.
Yeah. So that completes this week's night sky news and what we've managed to get from the gallery.
Thank you very
Lovely
much.
images there. Thank you, everyone.
That's just wonderful. Okay, so thank you all very much for your images. As always, don't forget that not only do they appear here on Tuesdays, they appear on your own gallery on the Space Oddities website, which, as always, is https spaceoddities.space. And before we go any further, we are going to have a quick word from our sponsor. This video is sponsored by Picastro. It's like Instagram for space nerds. Thank you to Tom for sponsoring Space Oddities, as always. Don't forget as well, if you want to send your images into our gallery, then attach them to an email, 1 image per email, please, and mail them to gallery@spaceoddities.space. And we always enjoy looking at your images. So thank you to all our regular contributors, but we're always looking for new contributors to the gallery. So if you've taken anything you would like to share with us and our esteemed viewers, then please send them in to the gallery. If you would like to support Space Oddities, you can do so, first of all, by buying us a coffee, which is a good way of doing it. So you can either click the link that's appeared in the chat or scan this QR code, which will take you to the Buy Me a Coffee page, where you can contribute to keeping our caffeine levels maintained. We might put up a new QR code next week by Dave a Laptop, so we will have to wait and see. Also, if you would like to make a direct contribution to our coffers, then you can do so by clicking the super chat icon underneath the chat window. And that's the one with the $sign on. That will allow you to make a donation directly. Now, in terms of other things that we can offer you, you can, of course, because it's the season, buy a Space Oddities t-shirt. They are £20, including UK postage and packing, so very good value, very good design. I think the person who created that design should get some sort of reward. And you can again click the QR code or scan the QR code or click the link under.
Dave's modeling the t-shirt.
A lovely, pouting, gorgeous model this evening. Rachel is modeling the Space Oddities. We also have the Space Oddities hoodies available. They are £40 again, including UK postage and packing, and they come in two types: a zipper hoodie or a pull over the head one. And obviously, with the zipper hoodie, the design is on the back rather than the front, because that makes perfect sense. If you are ordering from outside the UK, please add £10 to the total value of your order to cover the postage. So there you have it. So that's how you can support us. And we're going to move on now. In fact, we're going to go back to Roger, and Roger is going to be telling us all about something very dear to his heart. It's not alcohol. It is, in fact, Mare Crisium on the moon, because, as we all know, Roger is a fantastic lunar photographer and never ceases to amaze us and impress us with his moon photos. But he's put together something about a region of the moon that certainly moon observers are familiar with, and moon photographers are intimately familiar with, and that's Mare Crisium. So over to you, Roger.
You're muted.
Yeah. Okay.
Hello.
Hello.
Yeah, we can hear you now. A little voice out of the dark.
Right.
Oh.
Can you hear me?
Yeah.
We can hear you, Mother.
Yeah.
All right. Okay. Right. So this is the start of a series that I'm planning on doing. Please give me some feedback if you want to hear more about the various mares and other features of the moon, if you're taken with this first one. So let's see how this goes. All right. So here we go. Mare Crisium. So here we go. Oh dear. Right. Okay, so here we go. It got its original name in 1651. Mare Crisium is the Latin for the Sea of Crises. So we'll find out most of the lunar features that are here are all in Latin, as you're probably all aware. So there was a previous name of the Caspian Sea, which was used by Harriot and Gassendi due to its position on the moon, position on the Earth from the Caspian. So as we can see, where it is, it's over on the eastern limb, highlighted here in its position, just like that. So obviously quite nicely positioned during the early phases of the moon. It's roughly 556 kilometers in diameter, covers a surface area of 176,000 square kilometers, and the basin rises at 4 kilometers from its point, highest point. So it's a fairly flat area, and they have a lot of little wrinkles which have got lots of different names from various people. We do have quite a few craters around the area: Promontorium Argyrum, Yerkes and Lick, as also named after various observatories in the USA. We've also got Picard, Pierce, and Swift, and also we've got the Proclus ray system, which is quite distinct on the western side of the Mare. So we've got an elevated rim all the way around, and then we've got the depressed area. So how did this all start? Right, the formation. We've started with basically from an asteroid hitting that area, like this, and obviously created a great area of, as you can see in these AI-generated images. And then we've also got some of the volcanic areas around the area around here as well during the construction and history of the formation of various seas around the lunar surface as well. But this is quite an interesting gravity map from the Grail data, which was covering various areas around the surface of craters and the mare as well. So it will give quite a good impression, and obviously for lunar landing sites as well to be aware of as well. So we've got various. We've got a mystery here in the topical over 500 and 150 kilometers, which in the Chrysium's central area, and this has been confirmed by the Lunar Prospector and the Grail mission as well. So we've got a bit of an anomaly over in that area for some reason or other, but we're working on there. Now, during the Apollo astronauts walking on the moon on the 21st of July, 1969, Luna 15 was due to land in Mare Crisium, but it didn't do very well, and fortunately it crash landed. But it seems to be a coincidence that it was landing in that area on the same day that Apollo 11 was actually on the surface. But fortunately, Luna 24 on the 22nd of August managed to successfully land and returned 170 grams of lunar soil back to the Earth. So that's the landmark in robotic sample returns. Now, I don't know if some of you people are aware, but this picture of the Luna 15 looks a bit like Dusty Bin from 321. Does it not?
It does.
Yeah.
Isn't that the Lunicod rover?
Yeah.
Yeah. But this is the one that managed to return the sample, Luna 24. So it drilled 2 meters down into the surface to get this.
Yeah.
And that was in 1976. So it's 50 years ago. So that's quite interesting.
Yeah.
So we're still obviously with the Lunar Reconnaissance Observatory still doing observations and mapping around it. Chandraman has managed to do a volcanic mapping of the minerals around there as well. So we've got Cayugu. This is also doing compositional analysis through multispectral imaging. And then we've got the Arecibo radar, which was detecting materials mantles by ejecta. So lots of surveys going on with the moon in general. So it's been quite an interesting thing. So they've been trying to get some radiometric dating from the lunar samples. So it's 3.34 to 3.45 GA. So that's
billion,
billions of years old. So, but some of the crater degradation's been in a more range of 2.5 to 3.65 billion years. So we can get to see where we've got such a difference in the surface there. So here's a heads down view looking straight down over the Mare Crisium. So not a very big sea, but quite interesting to know about. And that's the first in maybe a series of various seas and features of the moon.
Thank you very much, Roger. Very, very interesting. And
it's a very interesting area because at some point during this cycle, it's also called the Golden Ring.
Oh, really?
When the sun catches it, and on the inner circle of the actual crater. And isn't there, Roger, somewhere along the Alpine Mountains, an area where at certain times they say that they can see a lady's face with long flowing hair?
Yes, there's quite a few different features that you can see as well on other craters as well.
Yeah.
Just depending on the angle of the sun as it comes across to the peaks of the various craters. Yes,
Yes.
I can probably do a tour around the moon of all the different features that have been named after different sightings of what people can actually see of the features there.
Yeah, that was very interesting. It is one of my favourite areas, I must admit, of the moon. There's something about it.
Yes.
Okay, so there we are. Mary Cuisine, and if you would like Roger to give you similar information about other areas of the moon, then put it in the chat. And if you don't put anything in the chat, we'll assume that you don't want anything. So and you know, Roger will cry. So you know,
or I'll just do it anyway.
So Ian says, I don't know much about the selenology of the moon. Is that the term? This is promising. So there you are, Roger.
Oh, right.
Thank you for that, Ian. As
yeah,
always.
no, that's the right term. Yep.
Yeah, it is exactly the right term.
That's where you get the Hellenic cycle and all that from. It's on the moon and that. So,
okay, well, we're going to go back and try Lou's presentation again, just to remind you in case you weren't with us earlier. Lou's going to be looking at how we can actually observe the atmospheres of planets orbiting other stars. So let's have a look at this and see what happens.
Okay, so far so good. I'm tempted to stop right here and claim victory, but we'll just have to see. All right, come on, baby.
No.
Oh no.
All right, let's see if I can run it from my laptop.
Okay.
Let's do it that way. That's how frustrating.
That's really weird because it's just really weird. So anyway, while you're setting that up, another thing that we're going to be doing with the channel on Tuesdays is that to reduce the amount of time we detain you on Tuesdays, we're just going to be doing one presentation per week. And, you know, you will get to see all of them, but we're going to cut the time down to one major presentation per week, and just to, you know, make it a bit shorter for you. And that's what we're going to be doing as from next week. So we've got a few other changes coming up that we will let you know about in due course. But it does mean that our live streams will be shorter, but hopefully packed full of the same juicy goodness that we are world famous for. So there we are. Okay, right, Lou. So
I'll give it a try here.
Yeah, give this a try.
Slideshow. Alt tab. Where are we here? We are here.
And Andy Cowley says we like more. So yes, please go ahead and make it so, Roger.
Make it so.
All right.
Stuart says very interesting, and I enjoyed that, Roger, said Derek.
Is that working?
Hang on.
I'm just waiting for it to come on.
Let me put it on the screen. And have we got anything on the screen? Just 1 second. I just want to see what's going on here. Right, let's try this. 1 second. Right. Okay, so let's try this. Lou?
I'm here.
It's on the screen.
You're up.
Okay, let's do it. There's slide 1. I see slide 2.
Yeah, fantastic.
Yeah.
Okay, great. Well, let's see. The thought that there might be life outside the Earth, planets around other stars, is not recent. You can take it all the way back to the 4th century BCE. Democritus, who was an atomist, he believed that the universe was made of small elementary particles, and there are an infinite number of them. Therefore, there are an infinite number of ways to put them together. Therefore, there are an infinite number of other planets, perhaps some like our own. We can skip forward to about the 14th century, where my hero, Giordano Bruno, he was brave and a bit cocky, but both put them together and you've got something, perhaps a world leader. He believed that stars are suns, just like our sun, and they may have planets and they may have intelligent life around them. And he was burned at the stake for his spiritual beliefs. And I'm strongly encouraging the scientific community to stop that practice today. But since then, we have discovered, verified over 6,000, I think it's on the 6,200 or so planets around other stars verified. And there are 8,000 other planets that have initial identifications and are waiting to be confirmed, sitting in the wings. So this is a remarkable acceleration in knowledge. And as new telescopes come online and new methods and new detectors, there is certainly more to come. Well, so we have planets around other stars. We know this now. They are trillions of miles away. And it was thought for so many years that it would be impossible to detect them because the stars are bright, the planets are dim, they don't give off any light of their own, and they're small, and their distance just made it absolutely undoable. But in fact, not only can we do this, there are something like 8 or 9 detection methods to find mostly indirectly planets around other stars. There's astrometric detection, radial detection, transit detection, direct imaging, spectroscopic detection, all kinds of ways, creative ways that astronomers have figured out to detect planets around other stars, and more recently, to actually be able to analyze the elements of in their atmosphere. So how is this done? Well, this is a transmission spectroscopy, and the idea here is that the planet, if it is a transiting planet, in other words, if its orbit is on plane with our line of sight, moves in front of the star, and so the star's light moves through the planet's atmosphere, and the planet's atmosphere is cooler than the star. So the star's spectrum, the star's radiation, provides the background or thermal continuum for the spectrum. And because the planet's atmosphere is cooler, you'll see the signatures of molecules and atoms in the planet's atmosphere in absorption. So over on the right here, in the lower right-hand part of the screen, we see these deep absorption lines, and we know they are from the planet. And above, we see the light just from the star with no deep absorption lines. Okay, so that's one method. This is emission spectroscopy. Here we take an image of the spectrum of the planet and the star, and then we wait until the planet moves around the star, which is called a secondary transit or a secondary eclipse. And we take that image, and then we subtract the two. And from that, we get, so we have star plus planet minus star equals planet. And we get the emission spectrum of the planet. Here we see these lines in emission standing above what would have been the star's black body or continuum spectrum. So they're just two very effective ways of detecting the composition of atmospheres of planets around other stars. And this is direct detection. But from this, we can get temperature profiles of the spectra. We can get dynamics and wind speeds and pressures, all from the physics that we put together to model these signatures, these spectral signatures. Now let's see here. So here we have the first detection of an atmosphere of a planet around another star. And this was the very famous, y'all go to sleep with this. You wake up thinking about it, HD 209458b. Just keep saying that. That's a very prominent exoplanet in exoplanet discovery history. And it turns out that the Hubble Space Telescope was successful in detecting sodium in the atmosphere of this planet. Now, I'll probably say this more than once. Molecules emit dominantly in the infrared because their rotation and vibration lines emit at those frequencies in the infrared. Atoms emit most prominently in the ultraviolet or visible part of the spectrum. All right, so we have a sodium detection here by Hubble, which is dominantly, not entirely, but dominantly a UV and visible imager. Okay, Hubble can go a little bit into the near infrared and detect in that range, but here we have a single atom detection of sodium in an exoplanet from Hubble. And here's that detection. On the left, we see the star plus the planet, and on the right, in the blue, we see just the data points from the radiation, from the radiance of the star. So very clearly, you see the sodium feature here in absorption at about 2 × 10⁻⁴ what's a mole fraction relative to the radiance from the star. This is actually a little less than they had expected, and the modeling suggests that this planet may 209458b may have kind of a dusty or foggy atmosphere. There may be some clouds or other features scattering the light. Nevertheless, this was a sodium detection, the first detection of composition of an extrasolar planet. Well, there are a lot of technology, both space-based and ground-based assets that we have looking for composition of atmospheres and other planets' atmospheres. We have Hubble, obviously, in the upper left, orbiting the Earth. At the L2 point on the upper right, we have the James Webb Space Telescope. Down on the lower left here, we have the decommissioned, but very successful for its time, Spitzer Infrared Space Telescope. And then over on the right here, we have the VLT, the ESO, European Southern Observatory telescope complex. So we can detect this stuff from the ground and from space. And we're applying all these assets to learn more about these exoplanets, these 6,000 plus exoplanets that we've already discovered.
Hello.
Yes.
I'm sorry. Can I ask a question? I don't want to interrupt.
Go ahead.
You. How can you possibly do this from the Earth, from a ground-based observatory with the Earth's atmosphere in the way?
If you're looking, well, we have observatories at very high altitudes and very dry places.
Yeah.
Like,
okay.
Right. So you can get a little bit in the infrared there. In optical frequencies, obviously you can get some atomic identifications. Probably doesn't do too well in the ultraviolet. But we, as you know, Dave, the IRTF, the Infrared Telescope Facility, is on Mauna Kea at 14,000 feet. And you can also do this kind of work from the very dry air of the observatories in Chile. So that's really how you do it from the ground. Does that make sense?
I mean, I guess so. I was wondering if they had the same kind of a subtraction, which they must, right? I mean, they must be subtracting the atmosphere out at some level. They're looking at a dark sky or and then
I see.
pulling out the. Yeah, the spectrum. That's what I'm. I mean, that's what I'm talking about. You're looking through an atmosphere at another atmosphere that's, you know, how many light years away, and you've got to you've got to somehow get these.
You know, what's interesting about that is when I started at Goddard, when I was just a high school student, one of the first projects I worked on with Virgil Cundy, who eventually was the PI for the Sears infrared instrument on Cassini, was taking a spectrum of the moon from the Earth. The moon is a spherical black body with no, emission features or absorption features, and then taking an image, a spectrum of Venus through the Earth's atmosphere, and trying to divide the two to subtract out the Earth's atmosphere, which is all that you would see as you're looking at the moon. Turns out it wasn't too successful. But I think that's the kind of thing in the way that it's done.
Yeah. Okay. I guess I sort of guessed that, and I'm sort of asking maybe for the general audience too. But okay, thanks, Lou.
Yeah. So here we have identification of a few features for AA Tauri. Now, the observed data is in the top part of this graph. These are, you see dominantly 3 spectral features that are identified here. And on the bottom, you have the model, the theoretical model. So when you get on your computer and you write your software and you throw in your physics, say this is how molecules behave, this is the temperature of the atmosphere that we would anticipate with its vertical structure and pressure and scattering properties and so on. You say this is on the bottom part here, this is what we would expect to see. And then the observed data up top is what you actually see, and it matches pretty well. So C2H2 acetylene is in the red on the left, HCN hydrogen cyanide, a building block of amino acids, is in the green, and carbon dioxide. All 3 of these are potential biomarkers. And then the other features are water vapor. Taken with the Space Telescope infrared spectrometer. So I'm going to just show some examples of various spectra that were taken. This is James Webb, I think, exoplanet identification of water vapor in the atmosphere. So you see there's the vertical lines over the data points are the error bars, right? And then so the blue line here is the theoretical spectrum that would be expected if you're looking at water vapor. So we have catalogs of these, huge catalogs online now of these emission and absorption spectra from various molecules and atoms. And so we can line those up with the observed spectrum to see to be able to identify what we're looking at. So here's identification of water vapor in an extrasolar planet. This is from the James Webb Space Telescope. This is an emission spectrum of exoplanet VHS 1256b, right? So B being the first planet observed, perhaps the only, I'm not sure, observed for that planetary system. This is a combination of NIRSPEC, the near-infrared spectrometer, and MIRI, the mid-infrared instrument on James Webb. And so you can see, oh my goodness, so water vapor, carbon monoxide, okay, for you guys, methane, and silicates here. So lots of interesting atmospheric features that could indicate a habitable planet, perhaps. And all of this, as you combine the NIRSPEC and the MIRI data, go from about 0 to about 16 or 17 microns. More water features. This is exoplanet WASP 18b. I'm lying to you a little bit, because what you're seeing here is you're seeing these features in emission. They're humps, not divots, right? So these humps that you see in the spectrum are water vapor. And I just told you earlier in the presentation that we should be seeing molecular features in absorption against the backdrop of a much brighter and hotter star continuum. But it turns out what they've done is, and I don't know why Space Telescope Science Institute did this, but they've kind of inverted the spectrum so that what should be in absorption is here illustrated in, if it makes them happy, that's fine. So here again, water vapor identified in the atmosphere of an extrasolar planet. And just to be complete with this, I thought I'd throw up a couple of TRAPPIST-1 spectra. Here the data points are little green dots instead of little green men, and they have error bars in both relative brightness and spectral resolution, so you can see the error bars on the data. TRAPPIST-1D, E, and F are really indistinguishable from a planet with no atmosphere. You could make a case, perhaps, that it has a very thin atmosphere that might be consistent with this data, but to first order, it appears that those three planets excuse me, to have no atmosphere. TRAPPIST-1G, the jury apparently is still a little bit out, and so further observations are required. If it has one, is thin, it's cold, it's far away, the signal is very, very, very weak. So they're using some very sophisticated techniques to pull that out. And that means that the error bars are large, and so they have to be very careful about making these statements about what they've found. So TRAPPIST-1G apparently is out. Perhaps it has an atmosphere, perhaps not. And I think that's my last slide.
Right, thank you, Lou. Thank you very much indeed. I mean, to me, it's incredible that we can get these spectra at all. I mean, those of us that remember when the first exoplanets were discovered, it was the most amazing thing. But then, on top of that, being able to develop the techniques for actually analyzing the atmospheres of these planets, to me, it's amazing.
Yeah, I mean, further to Dave's point about ground observations, of course, we had observatories like Sophia, which flew in the belly of a 747 to get as high as the atmosphere as possible. We also had observatories on sounding rockets and high altitude balloons, so we were able to get some of the readings from those. But also, one of the questions that has popped up, and it was on earlier, is there was a debate going on about the naming of the TRAPPIST planets as B, C, D, E, and all that. And as Andy said, they're named after the distance from the host star. Well, of course, if you want to know when they were discovered, because they thought people were saying that they thought they were labeled when they were discovered, so they could be in different orders. But when Lou was talking about one of the planets and he had that long name, you'll find all the information about when it was found, when it was done, and all that in those numbers. So you don't get to sort of like, because it's TRAPPIST-1B, TRAPPIST-1C, TRAPPIST-1D, but when you get the name of the actual planet, usually linked with the star, it's all in those numbers. They're usually the dates and that when they were found.
Well, and go, if you're interested in all this, go to the NASA Exoplanet Archive. They have a tremendous amount of information.
I've already put a link in the chat, Lou.
Thank you. One more answer to your question, Dave. I know you know Mike Muma, right?
Yep.
And he was doing ground-based observations with IRTF on methane near the surface of Mars. And of course, there's methane in our atmosphere as well. So he used the Doppler shift. He waited till Mars was kind of not directly in line, but
in a larger relative motion to us. Yeah,
and he was able to identify those lines uniquely in the Martian atmosphere by by their Doppler shift.
That's good.
So that's another
Yeah.
method.
That's pretty cool.
Yeah.
All righty. And talking of Dave, because everybody does, of course. So we're going to go over to Dave now. He's going to talk about something completely different. So, Dave?
Now for something completely different. No, okay, now do you want me to try again, or did you? I don't know if you had. I uploaded mine, but I didn't know if you were able to. I also have another. I can try something different. So
Yeah, try something different.
all right, let me do that then. All right. So. All right. Share window. All right.
While Dave's doing that, we will be back twice more this week. Aren't you lucky, viewers? So tomorrow, SpaceX are launching the Falcon Heavy rocket to put a Viasat telecommunications satellite into orbit. We don't get to see Falcon Heavy launches that often, and they're always spectacular. So we will be covering that launch tomorrow afternoon. We will be here at 3 o'clock, and the launch is at 3:17. Was it, Daz?
Something like that. Just after 3 o'clock.
Anyway, we will be going live on Space Oddities at 3 p.m. UK time tomorrow, where we will bring you the hopefully the launch of the Falcon Heavy. It was scrubbed on Monday because of bad weather, so they're going to give it another go tomorrow. So we hope to see you if you can make it at 3 p.m. tomorrow on the channel. We will be back, of course, on Thursday, as I said, with Space News Weekly, our weekly news program, and I'll be publishing that on the channel sometime Thursday evening, not too late. So we hope you watch Space News Weekly and give you all the latest space news. So there we are. Right, Dave, how are we doing?
Are you not seeing it?
Hang on 1 second. 1 second. No, not seeing it at all.
Perhaps I should have looked at my astrological chart before I got on the show.
Yeah. Yeah.
All right.
Just give me 1 second. Just talk amongst yourselves for a moment. Let's see whether I can.
All right. While you're doing that, I'll see if I can try to share again. I don't know why it didn't at least share.
It did say you were sharing something, but I can't see it either.
Okay,
No.
that's odd.
No.
Okay, while we're talking, here's a limerick. Finish the limerick.
Oh, God.
A pretty young lady named Bright, whose speed was much faster than light. She took off one day in a relative way and
returned
previous night, right?
well done. Okay.
So nothing, huh? Because it's.
Well, I've managed to find it, and I've got it up for you.
You got it. There we are.
Okay. All right. So can I direct it, or do I tell you? Oh, now. Okay. Now we've got the. All right. I tried to put it as the slideshow, but I guess it didn't maybe like that. All right. Well, let me give one more try for the slideshow.
Okay.
And let's see. Is that, or maybe it's better if I do this. All right. How about that? Oh, well, maybe give it a second.
Yes. Well, we can see it now.
Is that like a full screen good picture?
No.
No. Wow. All right. Oh, you're not seeing anything.
Journeying through the universe.
All right. I guess I was hoping maybe I found a solution, but it looks like that's not. It looks like
We've
probably
got Apollo Quarantine Program, 1969 to 1971. But can you advance it, or?
Yes, sure. Yeah. So you're seeing it now.
We're seeing your actual PowerPoint presentation.
It looks like it's
workbox.
stuck. It looks like it's stuck.
Yeah, it does.
Yeah.
Oh.
All right. Well, listen. We will try and
advanced
sort that
it,
out. Perhaps you can present that next week, then, Dave. We'll try and get it sorted by then, if that's all right with you.
Yep. Okay.
Yeah. Okay.
Start the GoFundMe page quick.
Okay. Yes, I don't think our fund will stretch to buying you a new laptop by next week.
No, I think I'll have to take care of that myself. Thanks.
Yeah, I think so.
On the secondary market.
Lastly, this evening, we're going to go back to Roger because it's that time again. It's Constellation of the Week. Da, 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 da. So that was a pretty weak fanfare, wasn't it? So anyway,
Yes.
over to you, Roger.
As usual, we've got one of the larger constellations again, because I do. And we've got dig. Okay, so we're into Gemini. So it's currently visible at the moment, although it is gradually diminishing in the into the west. So there we go. Anyway, we've got some of the histories of the background of the constellation. Obviously, with the two main stars here of Castor and Pollux, and the Gemini, which is the Latin for twins. So there we go. So we've got the tale of two fathers, one which is Pollux, which was the son of Zeus and Queen Leda, and Castor, who was the mortal of the sun Leda and King Tyndareus. Hope I pronounced that right. Tyndareus, right. Okay, so onwards to the next. Are we lagging?
I've got slide 4 here.
Right. Okay. Right. Oh, here we go. So its position, I'm sure most of you know where it is. It's to the west of Orion, and down below Cepheus, and over towards Cancer, obviously. So part of the 12 well-known zodiacal constellations. It's part of Ptolemy's 48 constellations that he labelled up. So it covers 514 square degrees, so it's nothing like some of the larger constellations at all, and is best visible in February to most of our awareness. So there we go. So, as we go on, we do have a Messier object, Messier 35, which is down over on the eastern side of the constellation. It's 2,800 light years away and contains roughly 200 stars of magnitude 5, and is visible with the naked eye, although it doesn't look too bad in a pair of binoculars. So, but we've also got this is the Hubble picture, the Clown Face Nebula. I'm sure that was I wonder who named that one first. That's a magnitude 9.2, and that's roughly 4,000 light years away, and obviously named due to its concentric shell structure. It's also known as the Eskimo Nebula, which I'm sure a lot of people will find more familiar, and is quite an interesting object to photograph. I'm sure that Tom has taken some pictures of it and probably spent about 50 or 60 hours on it, like he does. So there we go. So it's obviously an interesting shell explosion from the star as it faded away towards the end of its life. So we've also got the Gemini meteor shower, which is can reach over 100, although that can be in disputes, but it's a more regular display that you usually get around December, around the middle of the month. So it is quite a popular one to see quite easily, and a more frequent shower. So we're just getting through. So we're getting through being a winter constellation. It's on the ecliptic. And there are 11 stars that host known exoplanets. So there we go, Lou. So so that's quite good. And there we go.
There
Thank
we
you
are.
very much.
Great. Thank you so much, Roger, as always. So there we are. So we're going to start wrapping things up soon. So just a reminder, we'll be back at 3 p.m. UK tomorrow for the launch of the Falcon Heavy putting of Viasat big Viasat telecommunications satellite into orbit. As I said, scrubbed on Monday because of bad weather. We hope they manage to launch it okay tomorrow. We'll be back for Space News Weekly. We will publish that on Thursday evening. And then, of course, we get to next Tuesday's live stream. So I'd like to say thank you to Michael and to Roger and to Dave and to Lou and to Daz. Apologies for the preponderance of technical problems that we've had tonight, but it happens sometimes. So we'll try and get those sorted for next week, obviously, if we can. And that's it. So we'd like to thank you all for being here. Don't forget to send your images into the gallery. That's gallery@spaceoddities.space. Put them in an email, send your galleries in, send your images into the gallery. And so if we don't see you tomorrow or you don't watch the video on Thursday, then we will see you this time next Tuesday on Space Oddities for another dip into the wonderful universe. So from all of us at Space Oddities, take care of yourselves, have a fantastic week, and we will see you very soon. Bye-bye.